Hello everyone, welcome to this video. In this video we'll be looking at the answer to this question, that what is group isomorphism. So basically here we are going to talk about the formal definition of isomorphism. So in the previous video we are quite moved by the examples that why we should study about isomorphisms. So let's study about isomorphisms in detail. Okay, so here we first of all define this thing, group isomorphism. It was initially given by the famous mathematician, which we pronounce by saying Galva and not Galvus, right, or Gallios, right. So the pronunciation is Galva. This mathematician Galva about 180 years ago gave this notation of group isomorphisms. The term isomorphism, this is derived from the Greek words iso and morph. Iso means same and morph means form. So the objects which are having same form, they are known to be isomorphic to each other, right? So this is how we use this term. So for the formal definition for group isomorphism, we say group isomorphism, it is basically a mapping, right? It is a function phi which starts from the first group G and ends to the second group G dash, the two groups which we wanted to compare, right, which are similar to each other, which have the same concept, same meaning, however use different notations or terminology. So phi here represents a mapping from group G to group G bar such that it is a one-to-one mapping, so it should be 1-1, right? One-to-one mapping from G onto G bar, so that means we have 1-1 property for this map, we have onto property for this map, and moreover it should preserve the group operation. Now what does it mean to be by saying it preserves the group operation? Now what does it mean? So let's understand this thing. So we have three things. We should have this mapping which should be 1-1 onto n, where the group operation is preserved. So here you can see the statement, we should have phi of A star B, where what is this star? Star is the group operation of G, and what is this circle? This is the group operation of the group G bar, right? So you see, you took two elements A and B from the group G, then you apply the group operation of G onto it and then apply the mapping. It would give you the answer as the mapping applied onto the first element and then the mapping applied onto the second element, and then we are composing these two according to the operation of the group G dash, right? So this is what we are doing here. So here you should note that the operation, this one, the star, and this dot, they are two different operations. They could be same, they could be different depending on what operation we can define on the group G and what operation can we define on the group G bar, right? So the operation on the left hand side of the above equation star, this is the group operation of the group G, and the operation, this circle in the right hand side of the above equation, is the group operation of the group G bar. So this is what I've been explaining to you. Okay, so we say if there is an isomorphism from the group G to the group G bar, then we say the group G and the group G bar, they are isomorphic to each other. This is one thing, and in notation we write this thing to be G is isomorphic to G bar. So this is the symbol here for isomorphism, right? So this is exactly the same symbol that we use for similarity or for defining the equivalence classes, right? So from the definition of isomorphism, it is also very clear that they have the same order. How this is so? Now to understand this thing, let's see this figure here. So we have some group G, so it is a set which is say accustomed with some group operations A star. This is another group which is accustomed with some group operation circle, right? So suppose we take two elements A and B within this group G, right? Then we compose these two elements. So suppose this operation is multiplication only, right? For this multiplication here, we are multiplying A and B, so we have another element which is AB, right? Now what we do under this mapping phi, this element A would go to the element here, this one phi, it would be phi of A. The element B here would go to another element which would be phi of B, and the third element AB would go to another element which would be phi of AB, right? Now if you have isomorphism, so that means each element here should be mapped to some element here. This is what it means to be 1 1, right? Another thing, for every element which is present in this G bar, it should has a pre-image in this G. This is also there. Another thing that we are saying is the element which the element AB which is mapped by phi, it should be phi of AB, but this is phi of A and the group operation of G bar phi of B, right? So this is the operation preserving property, right? So this definition can be visualized as I have told you here. Each element in G is mapped to a different element in G bar, and each element in G bar has a pre-image which we have some element in G, right? So that means for an isomorphism we require a mapping which is 1 to 1, it is onto, and it should preserve the group operation. So this is the formal definition of group isomorphism.